typically they want us to find instantaneous speed and instantaneous velocity. So remember from the average velocity between the time A and time B, the slope is that connecting line. What happens if A and B become closer to each other? So we can make them a little bit closer, and even a little bit closer, and a little bit closer until we get to the point where A and B are effectively the same point. So the time difference is really zero. There's just not much there at all. The line connecting A and B is a tangent line to the curve. And if we find the slope of that tangent line, that is the velocity at that very instant. So that is instantaneous velocity. So now we can go on to this problem. It says at point B, we want to know what is the instantaneous velocity. This is a little bit more difficult because if I draw the line and I end up trying to draw a tangent line, that tangent line might kind of look like this. That's probably about the best we can do. From that, we can get a couple of different points. So here's a 0 point here, and then we're going to say that here's our other point here. And we need to go through and do a little bit of math for this. So we've got a couple of different points on the x-axis for position. We have our final position, which is -2, and we're going to subtract from it 0, and then we're going to divide by our two values for time. Notice that we're getting about 0.55 and about 0.45, so the difference there is about 0.1 seconds. At this point, we can go ahead and do our math, and we see that we have about -20 meters per second. So that's a lot different than our speed or our velocity that we had before. So instantaneous is a little bit different, actually a lot different than what we had for average velocity, which was this line, slope of that line. And then remember when we did the average speed, we did several segments before we ended up with something. And so there's the difference there. If we go on, we can talk a little bit about average and instantaneous acceleration. If I draw a line going from A to B, the average acceleration is represented by the slope of the line connecting 2 points, and notice this is a velocity versus time graph. So slope would be a meter per second, then that would be the average acceleration. If I take that line and I make it tangent, that's instantaneous acceleration. It's just the slope of the tangent line on the curve of a VT graph. So that one's pretty simple too. At this point now I've got this funny looking thing here. The instantaneous acceleration is negative where the curve is concave down. Okay, so you see these concave is facing down. And the instantaneous acceleration is positive where the curve is concave up. So we've got instantaneous acceleration. What is it doing at this point? It is accelerating because you'll notice then it travels this way. At this point, it is instantaneous acceleration is trying to make it go closer to the origin, so that would be a negative instantaneous acceleration. Instantaneous acceleration is 0 with the slope is constant. So here we've got a constant speed, so we don't have any acceleration at all. This is kind of a difficult concept for people to get because it is position versus time, and that makes it a little bit different. If we look at an object that is dropped from rest and reaches terminal velocity, they want to know what would the velocity versus time graph look like for that. And so what we can do is just take a look, and you'll notice that if this thing is dropping from rest, here it's at rest, and it continues to accelerate in the negative direction until the velocity basically just becomes flat. So we have a constant velocity. And that's because it's reaching terminal velocity, where its speed going towards the Earth is a constant after some time. The next one, they want to know an object that is dropped from rest and reaches terminal velocity during its fall. This is a position versus time graph, so a lot different than our velocity versus time graph. Here you'll notice that we start at a certain position. We don't have a lot of speed. We pick up speed, so this is picking up speed in the negative direction because we have some lines that are tangent that are becoming steeper and steeper until you go to a point where it's just a constant velocity until it hits the ground, at which a point after it would stop. We can go on to the next slide. This one says estimate the net change in velocity from 0 seconds to 4 seconds. And notice that this is an acceleration versus time graph. So what I'm going to do here is I'm going to fill in the triangle, and anytime I want to go from acceleration backwards to velocity, if I just find the area under a curve, that actually will tell me what that velocity is. And the reason we can get velocity from that is we're taking a meter per second squared, and when you find the area, you're really multiplying the two together. So meter per second squared, we're going to multiply that times a second. Notice that one of the seconds goes away on the bottom. This second completely goes away, and you're left with a meter per second. So this area here is actually the velocity of that object. To do that, we've got to find the area of this triangle. We know that the area of a triangle is just 1/2 base times height, but here our base is time and our height is the acceleration. So I'm going to go ahead and put 1/2 AT. Now I'm going to plug everything in. So this is 0.5 times our acceleration, which is 1, and our time, which is 2. If I go through and solve for that, I end up with 1 meter per second. We talked about how the units cancel. For the other part, we're going to look at the upside down triangle, basically the same thing as the triangle that we have here, but notice it is below the line and our acceleration is -1. So if we use the same equation, we're going to do 0.5 times -1 times that same time interval, which is 2 seconds. So when you do that, you end up with -1 meter per second. So anytime you want to go from acceleration versus time to velocity, you just find the area underneath. Negative for the area under the curve, positive for the area above the median line there. And so that's pretty simple to do. We'll talk about that later as an integral, but right now you've not been through that in calculus yet. If I want to find displacement, we can do the same thing. We know that if I find the area of this shape here, so really we're going to split it into a triangle, and then we're going to split it into a triangle and then a box. If I want to find the area of the box and of the triangle, that's very simple to do. But if I have a meter per second and I multiply that times a second, so that's essentially what we're doing in the box, notice the seconds go away and we're left with meters. So inside of this is our area, which is actually the distance that this thing travels. So we could put D in each one of those. So let's go ahead and find it for the first one. We know that distance here is equal to 1/2 of the velocity times the time, or 1/2 of the base times height. So now we can go ahead and plug everything in. 0.5 times our velocity here, our height is 2, and our base is also 2. So 2 times 2 is 4, and half of that would be 2 meters. On the box itself, we're just going to use distance is equal to velocity times time, because our velocity is our height and our width is time. So we're going to plug our numbers in, and that would be 2 times 2, and that would be equal to 4. Now it said net displacement, so in order to find the net displacement, I'm going to take net displacement, so we'll just put net D is equal to 2 meters plus 4 meters, and that is equal to 6 meters altogether. So that is our net displacement from this graph. So it's a pretty simple process to do. You just have to get used to it. And like I said earlier on the previous graph, this is what we call integration or antiderivative. Same thing. And we're just trying to use a little bit of calculus without actually using calculus to find some displacements and some velocities. The next section, derivatives, we will save for the next video.